Hi, hello, welcome back to my YouTube channel. You have my introduction already. So today let's move on to the subject called electromagnetic waves. In electromagnetic waves, today my topic is about the Gauss law and its application. Now let's see the introduction to Gauss law. Gauss law is a fundamental concept in electromagnetism. It relates the electric flux through a closed surface to the total charge enclosed by that surface. Gauss law is a useful tool for calculating electric fields in symmetrical systems. Now let's see the statement of Gauss law. Gauss law states that the electric flux through any closed surface is proportional to the total charge enclosed by the surface. Mathematically, it can be represented as phi is equals to E into dA is equals to Q enclosed divided by epsilon naught, where phi is the electric flux, E is the electric field, dA is the differential area vector, Q enclosed is the total charge enclosed, and epsilon is the permittivity of free space. Now let's see in this figure we can see electric flux and Gauss law. Gauss law states that the electric flux through a closed surface is proportional to the charge enclosed by the surface. Let's see the formula. Closed surface E into dA is equals to 1 by epsilon into Q, charge of enclosed surface. We have epsilon. Epsilon is the permittivity of free space, where epsilon is equals to 1 by 4 pi k is equals to, the constant is 8.85 into 10 to the power of minus 12 coulomb square per Newton meter square. Now let's move on to the first application of Gauss law in spherical symmetry. Gauss law is particularly useful in calculating electric fields of symmetrical systems. For a uniformly charged sphere, the electric field outside the sphere is the same as that a point charge located at the center. Inside the sphere, the electric field is zero. As if we take the sphere, the electric field around the sphere will be as same as the electric field located at the center of the sphere. So the electric field around the sphere is equal to the electric field at the center. Gauss law allows us to prove that the electric field outside a uniformly charged sphere decreases with the square of the distance from the center. From the formula of electric field through a spherical symmetry, we know that E is equals to Q divided by 4 pi epsilon r square, where E is the electric field, Q is the total charge, epsilon is the permittivity of the square, permittivity of the free space, r is the radius of the sphere. And this definition says that as the electric field located outside the sphere will be decreasing as the radius of the sphere increases. In this formula, where radius is indirectly proportional to the electric field, hence the electric field decreases when the radius increases around the spherical shape. The electric field inside the sphere is zero because the charges within the sphere cancel each other out. The electric field inside if we take any sphere, the electric field inside it will be zero because the charges within the sphere cancel each other out. Now let's see the second application of Gauss law in infinite line of charge. Gauss law can be used to calculate the electric field around an infinitely long, uniformly charged line. The electric field is perpendicular to the line and decreases with the distance from the line. The electric field is inversely proportional to the distance from the line. As we have seen in the spherical, the formula is E is equals to Q divided by 4 pi epsilon r square. As the square of the distance increases, the electric field around the sphere will be decreasing. In this infinite line of charge, as the radius increases, the electric field will be decreasing. Because the electric field is inversely proportional to the distance from the line. The electric field is perpendicular to the line and decreases with the distance from the line. Gauss law allows us to prove that the electric field around an infinitely long, uniformly charged is directly proportional to the linear charge density. The electric field points radially outward or inward depending on the sign of the charge. The electric field may be positive or negative, outward or inward depending on the positive or negative. Now let's see the third application of Gauss law in infinite plane of charge. Gauss law can be used to calculate the electric field around an infinitely large, uniformly charged plane. The electric field is perpendicular to the plane and has the same magnitude at any point equidistant from the plane. The electric field is of dependent of the distance from the plane. Electric field in the plane infinite plane charge. The electric field is dependent as the independent of the distance from the plane. It is whatever the plane distance may be, the electric field doesn't dependent on it. It is independent of the distance from the plane. Gauss law allows us to prove that the electric field around an infinitely charged, uniformly charged plane is directly proportional to the surface charge density. The electric field points away from the positively charged plane and towards the negative charged plane. The electric field intensity in the infinite plane of charge is away when the plane is positively charged and towards the plane when the plane is negatively charged. And now we are at the end of the conclusion of this video. Now let's see the conclusion. Gauss law provides a powerful method for calculating electric fields in symmetrical systems. It relates the electric flux through a closed surface to the total charge enclosed by that surface. Gauss law has numerous applications including spherical symmetry, infinite line of charge and infinite plane of charge. As we seen, the many applications of Gauss law even in spherical symmetry, infinite line of charge and infinite plane of charge. As we seen in spherical symmetry, the electric field is dependent on the square of the distance, as in the formula E is equals to Q divided by 4 pi epsilon r square. The square of the distance, electric field intensity is inversely proportional to the square of the distance, whereas in the infinite line of charge, the radius is inversely proportional to the electric field. As the formula says, electric field intensity is equal to Q is equals divided by 4 pi epsilon r, where the electric field is totally dependent on the radius of the cylindrical infinite line of charge and infinite plane of charge, where in the infinite plane of charge the electric field is totally independent from the distance of the plane. Whatever the distance of the plane may be, the electric field intensity doesn't vary because it is independent. In infinite plane of charge, we'll come to know that electric field will be away when the plane is charged positively, and electric field will be towards the plane when the plane is charged negatively. I hope you guys have got some little information about the Gauss law and its application in various fields like symmetrical, spherical symmetry and cylindrical symmetry and infinite line charge and even in the plane charge. Thank you for watching my video. Please do like, share and subscribe.